Welcome to the ninth live session of the course Network Analysis. I hope you are able to hear me. So today we'll be looking at assignment number 10, which is on two-port network theorems. Um, and this assignment will be, today's live session will help you solve the assignment number 10, hopefully. So we will start and I'll share my screen. I hope you are able to see my screen. Can you confirm just once?
Yes, sir.
Okay. Thank you. So we'll be looking at two-port theorem. So just before going into the problems, we will look at some of the basic concepts. What is actually two-port theorem and what are the type of theorems that we get in this chapter rather or assignment. So basically here you have a network. So this network here is put into what we call a black box. So this is a kind of a black box. And here we have one port. So this is the input side. This is the
Sir,
input. Yes.
the screen is visible, sir.
My screen is not visible.
Yes, sir.
So what are you wanting to say? I did not get you.
Yes, sir.
Did you say anything?
Yes, sir. The screen is not visible.
Oh, my screen is not visible. Okay, okay,
Yes, sir.
okay. Sorry. I did. Okay, let me share it once again. Just a minute. Now is it visible?
No, sir.
Sir, for me it's visible, sir.
Okay. You try to join once again, Murshid Alam. Just try to
Okay, sir.
rejoin. There may be some problem with your net. Okay, so Manikananda, you can see my screen, right? Manikananda, you can see my screen, right? Could you just confirm it once again?
Sir, your voice is breaking, sir.
Uh, you can see my screen, right?
Yes, sir, I can.
So now is the voice clear?
Yes, sir.
Okay. Sorry for that. There might be some internet problem on my side as well. Okay, so we are looking at two-port theorems, and so we just have drawn a black box where this side is the input. I should not draw it inside, let me draw it outside. So this is the input, and we have another port or terminal here, which is the output. And let's say we have current I2, or rather I should draw it from the input side. So current I1 flowing, and the polarity, the potential difference at the input port is V1, and the current at the output port or terminal is I2 and the voltage is V2. So here you can say that, so basically a two port network is a network where the current enters through one port and it kind of leaves through another port. So if the current leaves to another port, then the direction of the current would be like this, right? But for our convention we draw it in this way. You can draw it in the reverse way also, just here there would be a minus I2, nothing else. Now there are different kinds of two port theorems, or two port parameters rather, and for gate as well as for this exam you will be dealing with four two port parameters. So number one is this Z parameter, or we call it impedance parameter. Why, we will shortly see. And here also there are couple of formulas which you need to remember while you are before you go for the exam. Okay, so basically in two port network what we do, we don't know what is inside the black box. So inside the black box, we don't know what is there, right? But we somehow, so using these two port parameters, using two port parameters, we relate input port and output port. Okay, so basically v1 I1 and v2 I2 we relate. So to relate this we have four parameters. First of them is Z parameter. So here the relation between the input and output ports are as follows. So we have two equations. So V1 equals to Z11 I1 plus Z12 I2, and V2 is Z21 I1 plus Z22 I2. So see here, basically these Z are nothing but the impedances. So the way to solve this problem is that first, I mean this kind of problems is that we need to, so basically here what are my independent parameters? The independent parameters are, I1,
Even.
I, hello,
Oh, sorry.
yes, yeah, Murshid, go ahead. Are you telling something?
No, sir. No, sir.
You can see my screen, right?
Yes, sir.
Okay, thank you. Okay. Hmm. So, please don't try to interrupt in between. If you have any doubt, I will let you speak after I finish. Okay. So, because this explanation will take some time, I want to complete it quickly and then enter into the problems. And this is a very important chapter of this course. You can expect problems, definite problems from this chapter. Okay. So anyways, returning to Z parameter, so these are the two equations. V1 is this and V2 is this, where the independent parameters are I1 and I2. I hope you know by independent parameter what we mean. So I1 and I2 are basically controlling these equations, right? So we have to know I1 and I2 to know the value of V1 and V2. That is why these are independent parameters, and the dependent parameters are V1 and V2. Okay, so this is I mean this is the equation. So therefore here we need to determine the Z matrix. So what is Z matrix? The impedance matrix. We write it as Z11, Z12, Z21 and Z22. So what is Z11? For finding Z11 we need to make I to 0, that is short this so so I'm sorry, open this side, right? Because if you are making I to 0, that means your Z2 is infinity, right? So you are basically open circuiting the output, right? So Z11 would be V1 by I1 when I2 is 0. Okay. Similarly, just a minute. Let me make space. Yeah. So similarly, what would be Z22? It would be V2 by I2 when I1 is 0. Similarly, Z12 is what? V1 by I2 when I1 is 0, and Z21 would be V2 by I1, right, when I2 is 0. So using these conditions, you can determine what is the value of these parameters. Okay. So I'll just stop for a short time and ask whether you have any doubt in this Z parameter, and that in general the two port theorem what we have seen till now. If you have any doubt, you can speak up. Okay, I don't think there is any doubt, so I'll just proceed. So next is Y parameter, or it is nothing but admittance parameter. So Y is actually nothing but I by V. So Z was what? Z was V by I. So therefore so that is why we are calling this admittance parameter. Okay. So admittance is the inverse of impedance, right? So therefore we can write Y equals to 1 by Z or Z inverse. So therefore the equation will just change here, right? So this will be I1 equals to Y11 V1 plus Y12 V2, and the second one would be I2 equals to Y21 V1 plus Y22 V2. Now, so this capital Y, this admittance matrix, what we call this would be this thing, right? And similarly, in the same way, you can also derive. So Y11 would be what? It would be I1 by V1 when V2 is 0, right? So we need to short the output terminal, right? In this case, we need to just short this terminal and then determine what is the uh, Y11. So similarly, we also have the other parameters. So Y12 would be I1 by V2 when V1 equals to 0. Similarly, you can derive other parameters also, right? So therefore, we can write it like this. So since we have seen now that Y equals to Z inverse, so we can also write this admittance matrix capital Y to be the inverse of the impedance matrix. So basically this one, so capital Y is this matrix, right? We saw. So this would be equals to the inverse of the impedance matrix. So this is how these two parameters are related, Y parameter and Z parameter. Okay. I hope there is no problem in this. If you have any problem, you can speak up. So next is this T parameters, or transmission or ABCD parameters. So this has different name, ABCD parameters. So if you are doing electrical engineering, BTech in electrical engineering, or have done it, there is a subject called power system in electrical engineering. There you must have seen this chapter called transmission lines. So we have this. So in a transmission line, there are impedance, resistance, capacitance, like this. So this is basically the, so there is a bus, so this part, and uh, this part, right? So this is the sending end and this is the receiving end. So this is the sending end and this is the receiving end. So sending end basically means your the generating station, the thermal power stations that we are talking about. So this represents sending end, and this is the receiving end, which means our home or any university which is drawing the power supply. Okay, so here we represent, so this is we represent the parameters here using ABCD parameters or the transmission parameters. So that is why if you solve, if we try to determine what is the line loss, the transmission loss in the transmission line of the power system network, then we use ABCD parameters to determine that. So there this parameter is extremely useful. So therefore, what is the equation here? It is simple. It is V1 equals to Y, sorry, not Y. Really sorry. So this is A V2 minus B I2, and this I1 is C V2 minus D I2. So why minus? Because in a transmission line, so let us consider any transmission line like this, okay? And let's say that this is my sending end and this is the receiving end. So this is receiving end and this is sending end. So here we have a voltage which is V1, and here there is a current that is flowing I1, and here there is a voltage V2. And see, in a transmission line you can't expect, receiving end basically means the load, any household load or any hospital or any industry which is consuming the power which is being generated by the sending end. So sending end basically means the thermal stations, thermal power stations, right, which produces the power and sends it to the grid. This is the sending end, and the receiving end is let's say any school, university, uh, households, industry, this kind of thing. Okay, so here see, this receiving end, the loads at the receiving end will always draw the power, right? So therefore the current will always flow into the receiving end and not towards the sending end, right? So there is a situation, but in general we always see, logically the load will draw the current, right? Because here you are connecting a load, here there is a load here, so it will just draw the power, right? So therefore that is why this minus sign is here, because in the other cases here you saw that the current was I2, it was flowing into the black box or into the network, but here it is opposite, because in a transmission line the load always consumes the power, right? Any load that you connect, it will consume the power. So so that is why this minus parameter, this minus sign comes. I hope this is clear. I'll just stop and before we go to the last parameter. I hope this is clear. This is very simple. In the two port parameters now, you just need to remember these formulas, like for Z parameter, then Y parameter, and then T parameter. And also we have one last parameter, shortly coming to that. So last is the H parameter or the hybrid parameter. So if you have done the analog circuits there in BJT, you might have used this hybrid parameter. It is very useful to model the you know that AC modeling of the analog circuits, the BJTs, right? The common emitter amplifier C mode, those type of there you require these H parameters. So here this is what is the equation? This is H1 I1 plus H12 V2, right? And this is I2 is H21 I1 plus H22 V2. So here what is H11? It is V1 by I1 when it is 0. So the its unit is what? Its unit is ohm, right? Because it's voltage by current, right? Now what is H21? H21 is I2 by I1, right? When V2 is 0, and this has no unit because these are currents, right? So that is why you see the name hybrid parameter is given, because these has mixed units, you will see. So what is H12? It is V1 by V2. Again, this has no unit, and this is when I1 is equals to 0 because it's voltage, right? And this is H22 finally. This is I2 by V2, right? When I1 is 0. And this is ohm inverse, right? So that is why you see here this has mixed units. Ohm inverse, these two doesn't have any unit. So therefore, this name hybrid parameters has come. And the H matrix is given by simple, it's H11, H12, H21, and H22. Therefore now you can represent this as a matrix also. So this would be what? This would be H into this thing I1 V2. So this can also be written as V2. Sorry, this would be, I'm sorry, this would be V1, right? This would be V1. This would also be V1, and this is I2. So this is your H11, H12, H21, H22 into I1 V2. So similar thing you can also do for the remaining parameters. Okay. So this is in general the basic concept of two-port theorems. Now we will go into the problem. So here, um, sorry. So you need to remember these formulas particularly. So for Z parameter, this one, right? Then for Y parameter, this one. Transmission parameter, and this is the H parameter. Okay. So these formulas you need to remember, these four formulas, and once you do that, the remaining problem is easy. Now we will go into the problem and see how to solve that. It's very easy. If you solve a first problem, you will understand how to solve the remaining. These are easy, but you need to remember these four formulas. That's it. So I hope this is clear. Now we will be moving to the problems of assignment 10. If you have any doubt, you can speak. Tell. Am I audible and is my screen visible? Can anyone just confirm?
Yes, sir.
Yes, and visible.
Okay. Can you now hear me properly? Actually, the mic I was holding till now. Now I have put it a bit down. So, can you hear me now properly?
Yes, sir.
Okay. 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 So now we will be going into the problems, and these are pretty simple as well as interesting problems also. So just change the ink to black. So here this circuit is given, and we have to determine what are the h parameters, right? So we just saw this matrix and the h parameter, what are the equations. So as soon as you see the parameter, the basic step, the first main step is to write the formula. So it v1 equals to h11 I1 plus h12 I2, sorry, v2, and this is I2 equals to h21 I1 plus h22 v2, right? So this circuit is given. So here there is a dependent voltage current source, right? And you don't need to worry about this. Uh, I mean this, yeah, ohm inverse, because this represents conductance, right? Because since this is current, it's voltage by resistance, right? So basically V1 by 5 ohm, right? So that is where this conductance is given. You can ignore this. So we can make a simple transformation, source transformation, right? So if we redraw the circuit here, so this is the resistance and this is the dependent voltage source, right? And its polarity should be plus here and minus, because this is the current source is moving from left to right, right? So and so yeah, so this would be what, this would be 2 into zero point 0.2 v1, that is 0.4 v1, and this is 2, this is 3, and this is v1, this is I1, this is I2, and this is v2, right? Now so first we have to do what, in order to, so we saw here, so in h parameters, we need to first make v2 equals to 0, right? So v2 equals to 0, and now we have to redraw the circuit again. So v2 equals to 0 means our output is short circuited, right? Because v2 0 means your basically kind of current is infinity, right? And resistance is 0. You can take it other way. So v2 0 is output getting short circuited. So just redrawing the circuit here. So here the direction of I2 won't change. It should be whatever it was initially. So this is V1 I1. This is 3. This is 2. This is zero point 0.4 V1. Right now, see, we have two mesh here, and so this is the first mesh and this is the second mesh. And since this is short circuited, so basically there is no resistance to this path. So let me just use a different here. We will be applying KCL only, sorry, KVL. So through this path there would be I2, I1, and through this path there would be I2, right? So through this path I1 would be only flowing, and through this path I2 would be only flowing, because this is a short circuit path, right? If there was a resistance here, then a sum of I1 and I2 would have been flowing. You know this, right? So um Therefore, what is H11? H11 is V1 I1 when V2 is 0. So from here we can see we need to use the first mesh, right? So what is the KVL equation of first mesh? It is V1 equals to 3I1, right? And there is no resistance here also. So our H1 is what? It's nothing but V1 by I1. It is 3 ohm, right? So this is the answer to the first question. I'll just stop. I hope this is clear. This thing. If you have any doubt, you can ask.
Yes, sir.
Manikananda, clear?
Is that, sir, is that necessary to apply source transfer rule as the substitution rule? I mean, from current
See,
to voltage source.
yeah, I got it.
Because,
You, हाँ, बोलो.
sir, I done we can done this problem using this without changes, huh?
Can you be a bit more loud, Manikananda?
Sir, can we do this problem without changing this source as a current source into voltage source?
Yes, yes, you can do that.
Then why,
No
sir, we
problem.
are changing? Because I done without changing only.
No problem. I think, I mean, for me, I feel that the problem would get simplified because there is a single path. Other here, there would have been two paths, right? Because if you short it here like this here, there would have been two paths, right? So there would have been two mesh instead, or for KCL, if you would have applied, there would have been two paths. So from here one, and then this one, right? So instead of that, why instead? So that is why I did a source transform. But there is no rule that you have to do the source transform. You can do it in this way also, no problem.
Okay, sir. Sir, while doing that problem with the current source, I am having some doubts regarding to that current direction, sir. So only I willing. I mean, I'm planned to ask that doubt, but because of you changed this to voltage source, I can't able to ask that.
See, let us solve this using the source transform without doing source transform. And see, that is why I was telling you, na, it will simplify the analysis. Because otherwise, I know here there would be some confusion. Anyways, let us try doing this for to get your doubt clear. So I'll just draw it here. Okay, let us draw it here. So we have what? This is the circuit. So what do we need to find? We need to find H11, which is V1 by I1. Okay, so you have, see, for the first thing, you don't have to do anything, right? Because I mean, see, H11 is what? It's V1 by I1, right? So um basically, you short this at the first case, and um, this is 2, this is 3, this is I1, and this is V1, and this is I2. So here you see I1 would not go into this path, right? Manikananda, it won't go into this path. It won't flow into
Ah,
this
yes, sir.
path. I1. Why? Because this is a short circuit path, and current, and this is the least resistant path. So therefore, current would be taking the least resistant path. So simple, you do a KVL here, and you get V1 equals to 3I1, right? In this way, you get H11 equals to 3 ohm, right? You understand? You did you understand this?
Yes, sir.
Okay. Okay. So now, what is I2 and I1, right, relation? Because if you see the equation, we have this what. So if I just take you up, so we have this thing, right? Because when V2 is 0, I2 equals to H21 I1, right? So therefore, um, I21 equals to H21 I1. So we need to find out what is the ratio of I2 and I1, right? So for this here, let us now apply. So let us just erase this part for simplification. Yeah. So we need to now apply KCL here, right? We need to apply KCL through this path. So let us consider this as a node. Basically, there would be see this becomes more complex. So let us consider this as a node. This is one, and let us take this as grounded or reference node. So basically, current would be this. This is I2. So this would get divided into, let's say, I2 dash and I2 double dash, right? And then it would flow into this thing. So I2 is I2 dash plus I2 double dash. So I2 is I2 only, and I2 double dash is what? It is minus 2V1, and see what and this is, let's say, so this was this polarity, that polarity of this part here, it was V2, right? This was V2 by 2, right? Because this initially, this circuit here, this had V2 potential. Now you are grounding, you are shorting it, not grounding it. You are shorting it. The moment you short it, this point is connected to the ground because this is grounded. Therefore, this point is zero, or V2 is zero, right? And we also assume that. So V2 is zero. So therefore, you directly get what? I2 equals to minus 2V1. I hope I am correct. Yes, I think so. Okay. So I2 is minus 2 V1. Now we know what is the relation between V1 and I1. So we can just replace this here. So I2 would be what? It would be minus 2 into 3 I1. Right? So it is minus 0.6 I1. So therefore your H21 would be minus 6. Minus zero point 0.6. Okay. So did you understand this? We will verify using this thing. Okay. I'll show it here. But did you understand this thing? This how did we get Manikananda? Did you understand
Yes,
this
sir.
analysis?
Yes, sir.
Okay. So why this I2 V2 is zero? You understood, right? And why aren't we taking this node here? Because this is a short circuit path. If there would have been any resistance here, then we would have been taking this resistance also, right? This simplifies our analysis. Okay. So this is H21 is equal to zero point 0.6. Now let us also try to do this in the by using source transformation, right? So here, what we will do in this loop also, we will try to apply KVL. So what would be our KVL equation? It would be zero point 0.4 V1 equals to minus 2 I2. Why minus? Because this and this plus and this, the direction are opposite, right? If this would have been this, then this would have been plus. Simple. So here we are getting this relation only, right? So therefore, uh, right. So I2 is minus 0.6 I1. So therefore, what is your H21, right? It is minus 0.6. See, this analysis is more simple because you just have one equation here, and here, you know, you need to do this, first write this, then do this, and then you see that V2. I mean, this will do, but this will take more time. So what my suggestion is, when you see a current source and a resistance which is connected between this ground, so if we ground this, so this whole part is grounded, right, because this is shorted. So when you see any circuit like this, na, that any circuit like this, so this is a current source and there is a resistance, you always try to apply a source transform and just take it once whether this solves your problem or not. Okay, this is my suggestion. This will improve the analysis. There would be less chance of making mistakes. Okay, so I hope you understood this, Manikananda.
Yes, sir.
Okay, so now, so see, we have found out H11 and H21. Now we need to find out H12 and H22. So for that, see, using this equation, now we have to make I1 equals to 0, or open circuit input terminal, right? So the same thing here. There is a resistance. We will try to solve it both ways, okay? And then verify, Manikananda, for your convenience. So this is 0.4 V1, this is V2, this is 2, this is 3, and see, I1 is 0. That doesn't mean that V1 is 0, right? Because there is a dependent source here. So therefore V1 can't be 0. You just can't write V1 equals to 0. So therefore, see, here what we can do for finding out, I mean, getting a relationship between these two parameters, you can directly apply what you call a KVL here. So our V2 would be what? V2 would be, um, see here, this would be zero point 0.4 V1, right, plus 2 I2. Now, so 1 minute. Now, how to find out V1 and I2, right? Because we need to get a relation between your V1 and V2 and I2 and V2, right? Then only we'll get these two parameters. So, okay. Now let us apply a KVL in this equation, this mesh. So this mesh is open because I1 is 0, but let us apply, right? So see, this is very interesting. So what is the KVL here? So it is 3I1 plus there is no resistance here. So therefore we can't write I2, right? And since this is 0, therefore V1 is 0, right? And now you can substitute this here. So therefore V2 would be equals to 2I2, and your um, H22 would be what? So H22 is I2 by V2, which is 1 by 2.5 ohm inverse. And what is your this thing? V1 equals to H12 V2. Now this is, we just found out this is 0, therefore H12 is 0. And hence what would be our H matrix? So this is 0, this is zero point 0.5, this is I think point minus 6, minus zero point 0.6, sorry, and this is 3. So this is our H matrix. I hope this is clear. Now we will try to solve using the current source without doing the source transformation. But I hope this is clear. I mean, why V1 is coming as 0, I hope this is clear. If you have any doubt, please do ask, because this is an interesting problem. Because the moment you ground this, things change, right? Because if there would have been a resistor, then the analysis would have been much simpler. I mean, in a sense, you don't have to think. It would have been simple. You apply KVL here, you apply KVL here. So if you have any doubt, you can ask. Guys, is it clear?
Yes, sir.
Okay. So let us now try to solve this using this thing. So here now, what would be the circuit? So there is a I2 flowing. There is a point to V1. This is I. This is 2, and this is V2, and this is V1. And this is 3, and here I1 is 0. So see here, um, what we can do. So let us apply KCL at this point, right? What is the potential at this point? This is V2, because this is this point only. So let us say that this, again, this currents are two currents, right? So I2 equals to I2 dash plus I2 double dash. Now I2 is what? It is minus 2 V1 plus V2 by 2. Now V2 is not 0, because there is a voltage source connected. Previously it was grounded. Therefore this was 0, right? And in the other loop, we just simply apply what you known as KVL. So V1 is 3 I1. Now I1 is 0, therefore V1 is 0. You substitute this here, so it comes V2 by 2, right? So therefore H22 is I2 by V2, and this comes to be point. So this is also simple, but here I feel, to me, doing a source transformation here is more comfortable. I feel more comfortable. But anyways, you can do like this also. There is no problem. So Manikananda, Murshid, are these two this clear here for you too?
Yes, sir.
Sir, one doubt, sir.
हाँ बोलो.
Sir, I1 equal to 0 now. If 0 means
हाँ.
you shorted there are open circuit, sir.
This is open circuit.
Previously, okay, sir. But in open circuit, if you apply from the port 2 now, definitely the voltage will build now, sir, at the output.
Manikananda, I have opened input terminal V1. V2 is not open. There is a current
V2
I2
is
flowing.
there now due to V2, V1 having some potential now, sir.
No,
That
how?
is not V1 potential. Huh?
No, you see this loop, na? This is the first loop
Oh,
here.
okay, sir. Okay, sir. It's grounded.
So this
Okay,
is
sir.
shorted. So here I1 is 0 means V1 is 0, right?
Okay, sir. Okay, sir. Now I
You
understand.
understood, na?
Yes, sir. Yes, sir.
Yeah. So see, that is why doing this source transformation is easy, because you don't. The analysis is very simple, just straightforward. I hope you understood why you need to do a source transformation. simplifies the analysis. Okay. So this question is very interesting, and you can expect this kind of questions in GATE also. Okay. So just give me 1 minute. Let me just drink water. So see here. mm, Two-port networks, right? So basically, this black box 1 and black box 1 and black box 2. So this is 1 and 2. These are connected back to back, right? And here you have, so you have two ports. Why? Because this is one port, this is another port. So again, for this circuit, this black box, this is one port, this is another port. So that is why you have this. So this is a two-port networks. I hope you understood why this is two-port and not three ports, because you see this is port 1, port 2, port 3. But for network 1 it has two ports, and for network 2 again this has two ports. So that is why this is two-port networks in cascade. I hope you understood this. Okay. So see here, if you see, this is a, if you match with what we have used. So these equations are given, IV equations are given for the first port and for the second port. And now there, so these are the three questions. So estimate the Thevenin voltage in from port 3, Norton current from port 3, and this thing, Thevenin resistance from port 3. So if you see the IV equations now, V1 and I1, if you compare with what we have in the H parameter, see here, it's V1 I1, right? And here also it's V1 I1, and this is V2 I2, this is also V2 I2. So these are nothing but ABCD parameters. So therefore, you, what would be your first ABCD parameter? This would be 5, 6, -8, -5. So this is what you call T1, and T2 would be 5, 6, -7, -6. Can anyone tell me why I have written minus here and not plus in the minus this 8, 5, and 7, 6? But anyways, it won't affect our analysis. But still, why this minus sign is written? Can
It's not
anyone of
correct
you tell
direction.
me? Yeah. Yeah, because see here, basically the ABCD parameters are considered to be when the current is flowing I mean from the sending to the receiving end. So here from this input to the output. So here what they considered, actually they considered I to be flowing this way. So you can do that, but then you here you need to replace this with minus. Anyways, you don't need to consider it here. I'll just erase it. So here, see, the problem is very simple. V3, right? We first we need to see what they have told. So estimate the Thevenin voltage. So at the output terminal. So when we apply Thevenin voltage, we open circuit. So Thevenin voltage में what we do, we open circuit the output terminal, or what the terminal across which we want to calculate the Thevenin voltage, which means my I is 0, right? So therefore, looking at this, I3 would be 0, right? Simple, because we are open circuiting port 3. So here we are open circuiting OC port 3. Therefore, uh, so therefore your I3 is 0, right? So this equation will change now, right? Why? So V2 equals to 5V3 and I2 equals to 6V3. I hope you understood this. I'll just stop here because this is a very interesting problem. Did you understand this? Why I3 is 0 and how we arrived at this equation? Guys, did you understand this? If you have any doubt, please do ask. Murshid, Manikananda,
Yes, sir, understood, sir.
Murshid, Alam, you understood?
Yes, sir, understood.
Okay. Okay. So now the problem becomes very simple because see, we have been given V1 equals to 70. So we just need to substitute here. So in the first equation, if we substitute, it is what? 70 equals to 5V2 plus 8I2. Now we have here what is V2 in terms of V3 and what is I2 in terms of V3. So you just need to replace it here. So 5 into 5 V3 plus 8 into 6 V3. So 70 equals to 25 plus 40. Can anyone tell me what is 20? No, it's 73. Yeah. So V3 is 70 by 73. Can anyone tell me what is 70 by 73? Quickly.
0.9581.
0.958.
Yes, sir.
So this is the answer to the first question. I hope you have understood this. So this is VTH at port 3, right? Okay. So now see, for calculating the Thevenin resistance here, we don't know what is. So see, from our previous live sessions that we saw on how to calculate Thevenin voltage resistance. So if there was a circuit like this, there is a resistor here, there is a resistor, there is again a resistor, something like this, and here you are open circuiting it. So you need to calculate what is the Thevenin resistance looking from this terminal, right? So let's say this is R1, R2, and R3. Then it would have been like RTH would have been like R2 plus R1 parallel R3. But here we don't know what is the circuit of this and what is the circuit of this. What is inside this network 1 and what is inside this network 2. We don't know. So that doesn't mean that we can't solve the problem. So there is an alternative way. This also we saw. So we can represent RTH as VTH by ISC. What is ISC? It is the Norton's short circuit current. Okay. So this we can. This is how we can do. Now for doing finding out, so this should be done at port 3, right? At port 3 because everything is related to port 3, right? So you see here, if we solve this, we will also get the answer to this, right? Estimate the Norton's current in the direction of I3. So in this direction only from port 3. So here, let us first find out what is port 3 ka current. So see, for finding out Norton's current, we need to short circuit this, right? And here I3. So therefore V3 would be 0 because if we shorted the potential at this node would become 0. So therefore our V3 would become 0 and this would get reflected in these two equations. So therefore your V2 would be equals to V3 would be 0. So this is 7I3 and I2 would be what? It would be 6I3, right? Now again we need to replace this into this because it's already mentioned 70. So 70 equals to 5 V2 plus I2, right? So 5 V2 plus 8 I2. So 70 equals to 5 into 7 I3 plus 8 into 6 I3. So therefore, this becomes equals to what? I3 35 plus 48. This is 10 8 53, I think. Right. Hmm. So can anyone tell me what is I3 70 by 83? Calculate quickly.
0.8433.
0.84
Double three.
double. So this is the answer to the seventh question, right? Because so this is ISC at port 3. I hope you understood this, guys. If you have any doubt, then ask. Manikananda, Murshid Alam, you understood?
Yes, sir.
Yes, sir.
Okay. So therefore, the next analysis becomes very easy. What would be RTH? It is VTH by ISC. So VTH was what it was, 0.958, right? And this is 0.8433. Can you calculate this thing? How much is the value of RTH?
1.136.
1.136. Okay. So this is the answer. See, I feel that this kind of problems are very interesting, but again, this is easy also. This is easy provided you know how to do. So see here, there was no application of any two-port parameters, right? We didn't apply any ABCD parameter, but this is a two-port problem because we don't know what is inside this network one and network. But here there is a application of Thevenin's theorem and Norton's theorem again, the basic concepts, right? So I'll just erase this quickly. Remove this. So yeah. So now let us go to the next problem. Just- So here again we need to find out what are these parameters. So we will try to do this quickly. So this problem is very easy, you will see, because we have solved kind of good problems previously. So this problem is easy. This is straightforward. So when you see that we need to find out the z parameters, the first thing you should do is write the equation z11 I1, z12 I2, uh, V2 z21 I1, and z22 I2. Okay. So now let us make I2 0 in order to calculate Z11 and Z21, right? So I2 is 0 basically means that this terminal is opened, right? Because there is no current. Your circuit would look something like this. See, Manikananda, this problem is similar to the first problem. If you carefully see, this is the source transform circuit of the previous problem. This is 3, this is 3. Can you tell me how this is similar? to the first problem. So I am talking about the first this problem. Especially this part.
So here also they done conversion, sir, from current to
Yes,
voltage source conversion.
yes. So we can do a simple source transformation. So something like this it would look like. So here there is a resistor, and here there is a yes, current source. Right. So in the previous case, this was shorted, but here there is a resistor. Remaining things are same. So this would be 5, and this would be 2v1 by 5. Right. So the problem is same. So now let us find out what is Viva this thing. So we need to apply KVL in the first mesh, right? And just remember that this is open, right? I2 is 0 here. So I2 is 0 here. So applying KVL in the first mesh, this is 3I1 plus again 3I1, right? So here we can also write 3I2 because I2 would be flowing, but since terminal 2 is open, therefore I2 is 0. So therefore this is 6I1. Therefore Z11 is V1 by I1. It is 6 ohm. So I hope this is clear, right?
Yes, sir.
Okay. Now
Sir,
what is Z21? So Z21 is nothing but V2 equals to Z21 I1. Now see how we calculate. So you considering I. So if you consider I2, what would be the equation? So this would be V2 equals to 2V1 plus 5I2 plus 3I2 plus 3I1. Right. Again, this I2 and I2 is 0. So this is V2, 2V1 plus 3I1. Now we just calculated what is V1, right? It is 6I1. So therefore it is 2 into 6I1 plus 3I1. We are just substituting 6I1, V1 equals to 6I1 here. So therefore this becomes 15I1. And therefore your Z21 is V2 by I1. It is 15 ohms. I hope this is clear, guys.
yes, sir.
Murshid Alam, it's clear, right?
Yes, sir.
Okay. So now let us. So we have found out Z11, and so this would be Z21, huh? Printing mistake. So Z21 we have found out, now these two parameters. So for that, we need to make I1 0. That is open circuit the input terminal. So I1 equals to 0. Uh, you have any doubt, anyone?
No, sir.
Okay. Okay. So this is. This is 5, this is 3, this is 3, this is V1, here I1 is 0, this is V2, and this is I2, right? So uh, your V2 is equals to I2 into Z22, which means you need to apply KVL here. So let us apply KVL in this mesh. So just also consider I1 also here. So arbitrarily we will be considering I1 also, and then later making it 0. So this would be V2 equals to 2V1 plus 5I2 plus 3I2 plus 3I1, which is 0. Therefore, V2 equals to 2V1 plus 8I1. Sorry, I2. Now you also write the KVL here also. So this is what V1 equals to. So I'm directly writing 6I1 because this is 3I1 plus 3I1 plus 3I2, right? So this is 0. Therefore, V1 equals to 3I2, and we substitute it here. So V2 equals to 2 into 3I2 plus 8I2. Therefore, V2 is 6 plus 8, 14I2. And your Z22 is V2 by I2. Your Z12, it is V1 by I2, it is 3. I hope this is clear, guys. Pretty simple. If you have any doubt, you can ask still. Nikananda, Murshid Alam, any doubt?
No, sir.
Okay. Please, if you have any doubt, you can ask. I'll try to solve the doubt as much as possible. So this is 14, and this is your what you call impedance matrix. Right. Okay. So now, if this is clear, we will quickly move to the last problem. And here we will see some concepts. So like what is reciprocity, what is symmetricity, we will solve. And we will also see a trick to directly calculate. So here we will apply, we saw now that y is equals to z inverse. We saw this, so we will apply it here to get. So here we will calculate z parameter, from that we will calculate y parameter. So this is the circuit. Um Now just give me 1 minute. Okay. Um, so this is the circuit here. So again, quickly write the equation. V1 equals to Zi1, Z1 to I2. V2 equals to Z21 I1 plus Z22 I2. So your so basically we will first make I2 equals to 0, that is open circuit, the in output side. But here you see there is one another mesh also. See here, what you can do now, guys. Do you know delta to start transformation? Have you done that before, or start to delta transformation? Like, so what I mean is this. So what is a delta circuit? It's nothing like this. So the transformer, if you have studied three-phase transformer, then you must have come across this thing. So this is a delta circuit, and what is a star? This is a star. So there is a relation. So suppose this is R1, R2, R3. So this is R1 dash, R2 dash, and R3 dash. There is a relation between each of these resistance. So I won't be going into that, but what you can do, so if you see this kinds of look like a delta, so you can convert that into star, and your analysis to some extent may improve, I think. But here we won't do that. We will use as it is the circuit, but you may attempt it later, delta to start, and then find out. You need to redraw the circuit. So okay, anyways, so let us now focus on finding out the z parameters. So this is 8, this is 3, this is 2, this is 6, that is V2, I2 is 0, this is I1 and this is V1. Now here let us consider that this is I3 because this is a mesh. Now we need to apply KVL in these two meshes, right? This is a simple problem, but this is slightly lengthy, nothing else. So what would be V1? It would be 3I1 plus 2I1 plus 2I2. I'm also writing I2, and this would be what, minus 3I3. Why? Because see, I1 is like this clockwise direction and I3 is like this anti-clockwise. Sorry, both are in clockwise direction, right? So that is why this would be cancelling each other, right? So that is why this is 3 I3, because I3 would be entering 3 ohm resistance to the right hand side and I1 would be entering through left hand side. So therefore this minus, and this is of course 0. So V1 is 5I1 plus minus 3I3. Now this is our first equation. Now let us write the KVL in the third mesh. So this is mesh 1. Now mesh 2 is what? This is what, or let us write all the resistance. 8 plus 6 plus 3 I3. Again this, see, this would be plus 6 I2. Why, you tell me? I mean, you can find out, I won't tell you. But anyways, this won't affect because I2 is 0, and of course 3I1. So this is 0, and this would be equal to 17I3 equals to 3I1. So we will just write 3I1 by 17. This is equation 2. We will substitute 2 in 1. So substituting 2 in 1. Therefore, um, here this would be what, V1 equals to I1. This would be 3 into 3 by 17. So this one would be 85. 17 into 5 is 85 minus 9 I1. So this is 76 by 17. So therefore, yes. So V1 by I1, that is Z11, is what, 76 by 17 ohm. Can anyone tell me what is 76 by 17, the value?
4.47.
4. So this is the value of Z1. This is one answer. I hope this is clear. This should be clear. Simple KVL. Okay. So this is clear now. So now we need to find out what is Z21. So Z21 is V2 by I1. So we need to write the KVL here. So what is, I mean, in this mesh, let us write, right? So what is V2? V2 is 6 I2 plus 6 I3, right? 6 both, 6 I2 plus 6 I3 plus 2 I1 plus 2 I2, right? The symbols are, I mean, the signs I won't tell you. You can easily understand. If you have any doubt, you can ask. I won't explain it otherwise because this is simple. You should understand it by now. 6 I3 plus 2 I1. So I3 we already found out. It is V2 equals to 6 into 3 by 17. 3I1 by 17. That's 2I1. So this is 18 plus 34 by 17. I1. So therefore your V2 is 52 by 17. Therefore your Z21 is 52 by 17 ohm. Can anyone tell me what is this value?
3.0.
3.058.
058.
Okay. So this is the answer. I hope this is clear. Right? If this is so, then now we need to make I2 I1 0. Right? So now your I1 is 0, and now let us draw the circuit again. So this is lengthy, I agree, but this is very simple. So this is the circuit. This 2, this is 6, this is 3, this is 8. So here I1 is 0 here. This is plus V1, V2, I2, and let us consider this like this only. In the opposite direction. Okay. So let us write the KVL in the second mesh, right? So this is KVL in mesh 2. So by mesh 2, I mean this mesh, right, where this V2, I2 is there, and third mesh is this I3 elements. V2 equals to 6I2 plus 6I3 plus 2I2 plus 2I1, where I1 is 0. Therefore, this is 8I2 plus 6I3. Now again KVL in mesh 3. What would be KVL in mesh 3? It is 8 plus 6 plus 3 again, I3 plus um, so this would be also plus, right? So this would be also plus. Mm, yeah. So this would also 6I2 equals to 0. So this would be how much? 17I3 plus 16I2 to 0. Therefore, I3 is minus 6I2 by 17. So let us write it as third equation. And this is fourth equation. So substituting 4 in 3. So this would be how much? V2 8I2 minus 6 into 6 by 7. So this would be how much? V2 817 minus 36. Can anyone calculate and tell me what is this value? 8 into 17 minus 36 divided by 17.
5.88.
is 5.88i. So therefore we get Z22 is V2 by I2. It is 5.88. And now finally what is Z12? It is V1 by I2. Now we need to apply KVL here in the first mesh. So this would be what V1 equals to 3I1 minus 3I3 plus, so you just write it. So this is what V1 equals to 3I3 plus 3, sorry, I1, 3I1 plus, so this would be minus, right? Because you know this would be minus. No, plus 2I1 plus 2I2. Right, so this is 0, this is 0. Therefore, this would be what 2I2 minus 3I3. And just substitute this 3 into your 6I2 into 17. So your V1 is how much? 34 minus 18 divided by 17I2. I did a mistake somewhere. Yes, so this, yeah, so this would be plus, right? Y plus, because this is minus, right? Basically this is minus, and I3 is minus 6I2 plus 17. So this minus minus becomes plus. So this would be plus. Right, so this is 52 by 17. So this is again we calculated this somewhere. Yeah, 3.058. I hope this is clear. So this is Z12 is 3.058 ohms. Right. So once you do that, now we will quickly write what is our Z impedance matrix. So this was 0.3058. This was also 3058. This was 5.88, right? And this was how much? I1 Z11 4.47. Now see, they have told you to calculate what is what is the y parameter. So one
Yes,
way you can do it like, see here. So what is the equation of y parameter? It's I1 y11 v1 plus y12 v2. You need to sort v2, then find out each of these. So it will take this amount of time. Rather, there is a shortcut. See, we found out that y is z inverse, right? Because z is impedance, y is admittance, right? So therefore this would be the inverse of this matrix. So that is where this problem was given. So therefore this is right. So I hope this is clear, guys. This part why we are doing.
yes,
I mean, yeah.
Yes, sir.
Okay. So now simple mathematics, right? So you need to, so basically you swap this, right? For a 2 cross 2 matrix you swap this, and there would be minus sign on both of these, right? I'm not going into the rules, you know. For any dimensional matrix, it is and there would be of course a transposition here, and we need to calculate the determinant, right? So 4.47 into 5.88 minus 3.058 square. So therefore your y matrix becomes 5 point, it basically remains the same because the diagonal elements this way are equal. Right. Mm, yeah. So can anyone tell me what is this value 4.47 into 5.88 minus 3.058 square?
Sixteen point nine three.
16.93. So now just divide it, right? So y by, so just let me do this. 5.88 by 16.93 is 0.347. This is minus 1.81. This would be also the same. This is 0.264. So this is your y matrix. So this is y11, y12, y21, y22. Okay. So that's it. Now coming to the last two questions. I hope this was clear. This was a lengthy problem. Of course, you can expect a lengthy problem in this kind of assignments, right? Which is of course simple, but it's pretty lengthy. So I hope this is clear. So now we'll be moving to the last two problems. So what is reciprocal circuit and what is symmetrical circuit? Right. So what is reciprocal circuit? So reciprocal circuit basically means that, let us consider this circuit here, right? Two port circuit, okay. One two port circuit. So basically, what is my Z12? It is V1 by I2, and Z21 is V1 by I1. So I'm just writing the Z parameters. This is I1 and this is Z22 is V2 by I2. Now, what reciprocal theorem says, or reciprocity says, is that, so a circuit is reciprocal provided the voltage at one terminal due to the current flowing through the other terminal, that is here V1 due to I2. Okay, the voltage at a single term at one terminal due to the current flowing in the other terminal is equal to, this would be, yeah, so this is equal to the voltage at the other terminal due to the current flowing in the first terminal. Okay, so basically your this, so in reciprocity this should match. So basically the voltage in the first terminal divided by the current in the second terminal would be equal to the voltage in the second terminal divided by the current in the first terminal. So this is reciprocity theorem. So when you apply this for Z uh, parameter, this is, if this is, so if Z1 equals to Z2, then you say that my network is reciprocal. Okay. So here in this matrix, you can easily see that, so this was Z, so this is Z12 is how much? It is 3.058, and Z21 is also 0.358. So therefore, uh, so Z1 equals to Z21 is 3.058. So therefore, the network is reciprocal. Okay. So this is the answer. So before moving to symmetrical circuit, I'll just ask, this is clear or do you have any doubt?
Sir, if the network input network is actually reciprocal means what does its real means? What it will do, the characteristic.
What it will do to the, I did not get it.
Sir, if the circuit is reciprocal means what we can get from that, sir? If we prove that circuit is reciprocal now, what we get from that circuit network?
Uh, See, I am, presently I won't be able to tell you the answer, but yeah, there is a inner meaning to that. So I need to look at it. Okay, I'll tell you maybe in the next live session. So there is a significance. So reciprocity and symmetric circuit, there is a significance. Okay, so I'll tell you. Basically, in terms of current flowing, amount of current flowing or voltage, there is a significance. So I'll check and let you know. Okay. At present moment, I can't tell you because I knew it somehow I forgot. So I need to check. Okay.
Okay, sir.
I'll check in the next assignment and tell you. Definitely. Sorry. So lastly, what is symmetric? So symmetric basically means, so basically in terms of this, you know, so your voltage, see, if you exchange the input and output ports, na, so if you make, if you make this V2 and if you make this V1, and also if you interchange the currents also, so if this is V2 I2 and if this is V1 I1, and even then the currents are same. So I mean af- after exchanging, so after exchanging these two, even if after exchanging this is V2 I2 and this is V1 I1, then your circuit is considered to be symmetric. So basically, in a way, this is V1 I1 equals to V2 I2, because in a sense they want to say that your input impedance and output impedance, it matches. Okay. So the inner meaning of symmetric circuit is that provided your input impedance and output impedance is the same, your circuit is symmetrical. Okay. So therefore, in here in Z parameter, it is nothing but Z22 equals to Z11. So that is the meaning of symmetric circuit. So if your circuit is symmetric, you mean to say that your input impedance and output impedance, it matches, nothing else. Okay. So in a way, you can also say that your input admittance. So if I write V1 by I1, I can also write I1 by V1 also, right? I2 by V2, because the ratio is the same, nothing else. So we can also say Y11 equals to Y22. So your input impedance, so you have any circuit, it has an input impedance, right? Input resistance. We previously we solved some problem. So there was a circuit, right? So they had told you what is the source impedance or source resistance. So here this I1 was flowing. So Z in was nothing but V1 by I1, right? So this is nothing but this source impedance or input impedance. So if this input impedance is equal to your output impedance, then you say that your circuit is symmetric. And also you need to interchange this, you need to exchange this. So at the input you need to bring your output parameters, that is I2 and V2, and at the output you need to make uh, I mean bring I1 and V1 and then check whether this is equal. So in a sense you are just trying to check whether your input and output impedance matches. So that is what you mean by symmetric. So here for this problem you see that Z11 doesn't match Z22 because these two are not same. So therefore Z11 is not equal to Z22. Therefore circuit or network is not symmetric. I hope this is clear. I will check what is the physical significance of reciprocal circuit, but at least I hope this is clear.
Yes, sir.
Okay. So I'll just check what is the significance of reciprocity. I'll tell you next with the phone. Okay. So
Sir,
yeah. Bolo.
can, sir, if the circuit is symmetric, now can we use the circuit in both directions, sir?
Yes,
It's
that is
input
what you
side.
are telling, no? Yes, exactly.
Yes,
You
sir.
can use.
Okay, sir.
Yes.
Whatever
See.
current voltage is
Yes.
applying
Yes.
in the both terminal,
Yes.
we will get the equal amount in that
Yes. Yes.
another
Yes.
terminal.
Yes. Exactly. Basically, you are see, your symmetric circuit means that even if you interchange the input and output terminals, then also your the current flowing to through each elements would be the same. So that is what you mean by symmetric circuit, right? That only happens when your input impedance and output impedance are equal, probably. I mean, that is what at least means by this formulas also. So yeah, so that is it for today. If you have any other doubt, you can ask. If you have any doubt, you can ask, or we will stop the session today. I will upload the video by today night, or maybe by tomorrow morning. And next week we will be looking at assignment 11. So I hope today's assignment will help you to solve assignment 10 of the current assignment, provided you haven't solved it and submitted it already. This will definitely help you. Okay. So if you don't have doubt, then we will stop.
Bye, sir.
Okay. Thank you. Bye. Good night.